Hello, everyone, and thank you very much for participating in this session. I'm Behzat and I'm a PhD candidate in UC Leuven, Belgium, together with my supervisor, Luca from UC Leuven, my colleague Sven from Transport and Mobility Leuven, and Mikey from TU Delft. We have developed, calibrate, and validate a large-scale traffic simulation model for the Belgium road network, and I'm going to present this work to you today. Let's start with the objective and motivation of our study. And I'm starting with the question of why we need a counter-scale traffic simulation model. As you know, there are lots of applications for counter-scale and large-scale traffic simulation models. For instance, we can evaluate the performance of the road network in different scenarios. And specifically in my PhD research, we would like to evaluate the performance of Belgium road network when we have connected and autonomous vehicles. So before that, we should first develop, calibrate, and validate the transportation model for the entire Belgium road network. So this is why we have developed this model. Okay, but how we have developed the transportation model of entire Belgium. As you know, for what we need for traffic simulation in large scale, like any other traffic simulation model, is to provide the supply data and the demand data. For the supply data, when it comes to using SUMO, normally we use the OpenStreetMap. But the problem with the OpenStreetMap is that, when you insert the map, when you extract the map from OpenStreetMap, it contains all of the types of highways and streets. But as we were working on the not the inner city traffic, and we were only interested in the highways between the cities, so it was not possible to directly extract the map from OpenStreetMap. So this is why we have used the Overpass Turbo, which is an extension to OpenStreetMap. And within this tool, you can indicate the types of highways that you want to extract from OpenStreetMap. So we have extracted the highways and provincial and regional roads from this tool, and then we inserted it into SUMO. And of course, we have done some manual revisions for having the perfect network in the SUMO. After that, it's time to talk about the demand data. As you are all aware, we have some classical demand models like the 4-step model, tour-based model, activity scheduling model, and so on. But the problem with these models is that they need very huge surveys. They need lots of data. But in the Belgium case, the problem was that the travel demand data was not available to the public. So this is why we came up with the idea of a probabilistic travel demand model, which needs low amount of data and which needs very, it doesn't need huge surveys in the country level. And I'm going to describe this probabilistic travel demand model to you. This probabilistic travel demand model only consider the yearly vehicle kilometer travel, the yearly truck trips, the population of the cities, and the distance between the cities as the input. Then based on this information, we calculate the total number of daily trips for the entire Belgium, and then we apply some random selection to the population and the distance distribution, and then we can have the hourly origin destination matrix. I'm going to describe this whole process in more detail, but before that, I would say that the core idea behind the model was that the larger a city's population, the greater its likelihood of being chosen as the origin city of a trip. And also, the more population of a city and the lower distance between cities increase its likelihood of being chosen as the city of destination. This logic is very near to the gravity model, but we have used this logic in a probabilistic manner, and this is what I'm going to describe. So the first step in our model is to determine the centroid. I mean, determine which cities we are going to consider, because Belgium contains 138 cities. So it's not possible to model each single city. So we have a selection criteria. I'm not going to describe the selection criteria in order to indicate the most important cities. And with that, we have selected 60 cities which were chosen as the centroid. So these cities can be selected as the origin or as the destination of the trips. In the second step, it's time to determine the total number of passenger cars daily trip in the Belgium. Here, the only input information that we have was the passenger kilometer travel per year in Belgium. So this information is available to the public, and we have add and as you may know, Belgium has 3 regions: the Wallonia, Flanders, and Brussels capital. So we have add these data together. So this will gives us the total passenger kilometer travel in highways equal to 85.7 cross 10 power to 9 vehicle passenger kilometer travel yearly in Belgium. After that, that number was the passenger kilometer travel, but we were looking for the number of daily trips. So in order to make this number to the number of daily trips, we had to make some, let's say, big assumptions. These assumptions was that each passenger travel 85 kilometers per trip, and also the weekend traffic is considered to be half as high as the weekday traffic. I know these assumptions might be very big assumptions, but we have tested this data. I mean, we have make a trial and error in order to have the best OD metrics. So this is why we came up with the 85 kilometer per. We came up with the assumption of 85 kilometer per trip. And after that, if you make these assumptions and based on this equation, then you can have the total number of daily trips in the Belgium road network. After that, it's time to work on the total number of trucks daily trip. Here, the only information that we got as an input was the number of yearly trucks trips which are loaded in Belgium and unloaded in Belgium. So based on these information and the assumptions that we made and this equation, then we can have the total number of trucks daily trips. So if we add these two information together, the total number of all trips would be 3.3 million trips in Belgium. So right now we have the total number of trips in Belgium. And the next step is to determine the origin and destination of each trip. In order to indicate the origin of each trip, we have formed the weighted probability distribution of cities' population. And then we have applied a random selection on this distribution. And based on that, we can have the origin of each trip. It means that this is the logic that I have talked in the first slide. This means that the more population of a city, the more its probability to be chosen as the city of origin. So we can, based on this distribution, we can have each trip's origin. After that, we should have each trip destination. In order to have each trip destination, we have formed the weighted distance distribution functions, the distance between the cities, and we already have the weighted probability distribution of cities population. And if we mix these two distribution functions, we will have the mixed population distance probability distribution function based on this equation. And then if we apply a random selection on this distribution function, we can have the destination of each trip. And as I said in the first slide, here the logic is that the more population of a city and the less distance it is between the origin city and the destination cities, the more its probability to be chosen as the destination of a trip. And here we have a calibration parameter, lambda, which determines the importance of considering the population or the distance between the cities when we want to determine the destination of each trip. And this is the calibration parameter which we have calibrated, and I'm going to describe the calibration process in the next few slides. After that, it's time to determine the departure time of each trip. This is very easy step because we have the typical hourly distribution of traffic demand, which is available in lots of resources and literature. So this is the distribution that we have used in order to determine the departure time of each trip. When we have these whole process will give us the origin destination matrix for the whole day, but right now I'm going to present the results of only the peak hour, not the whole day. And also, so when we have the origin destination matrix, and we have used the dynamic user equilibrium using the dual-iterate.py tool in SUMO. And also we have used the mesoscale simulation, of course, because it's not possible to run the microscopic simulation for the entire Belgium road network. So based on this information, we will have the base case model. But as any other base case model, we need the calibration and validation for this base case model. For the calibration process, we had two types of calibration. The first types of calibration that we had was the calibrating the traffic flow parameters. As you may know, the mesoscopic simulation in SUMO is a queuing-based model. I'm not going to the detail of the queuing model in SUMO. But we have used but in the literature, there are some works which calibrate the parameters of mesoscopic model in SUMO for highways. So we have used the same parameters as the works in the literature for the traffic flow model parameters. The next step is to calibrate the dynamic traffic assignment model parameters. In order to do that, we have used the traffic count data. And based on this traffic count data, we have adjusted the OD by the lambda parameter that I have talked in the previous slide. And also we have calibrate the dynamic user equilibrium parameters, like the number of iteration, the routing algorithm, the road choice model, and so on. So these are the calibration, these are the parameters which we have calibrated for our model. And this is the results of the calibration. We have tested 50 detector in the entire Belgium road network. And as you can see, the R-square for the simulated flow and the observed flow is very good. And also the gauge parameter is equal to the average gauge parameter is equal to 4.9, and more than 78% of observation have the Geh parameter less than 7.5, so which is in the accepted threshold. And after that, we have the validation of our model. In order to validate our model, we have used the distance matrix API of Google. As you may know, Google has an API for the Google Map, which is the distance matrix API, and which gives you the distance between the cities and the travel time between the cities for the peak hour or any other hour that you want. So we have done two types of validation. The first one is to comparing the distances, only the distances between the cities in kilometer. So on the left, you can see the distances in simulation in kilometer, and the distances in reality in kilometer are very near to each other. And each point, let me describe it in this way. We have, as I said, we have 60 cities, which can be origin and destination. So in total, we have 3,600 origin destination pair. And these are the distances in kilometer between each of these 3,600 origin destination pair. And on the right, we have compared the simulated travel time in the peak hour and the observed travel time from the Google Map API in the peak hour. And as you can see, also these validations gives us a good R-square and RMSE and so on. And yeah, here is the results of the model. As you can see again on the left, we have the simulated typical speed in the peak hour. And on the right, we have the real typical speed in the peak hour. And as you can see, our model, make the congestions in the right location, which means that, for instance, here in Brussels, in the north of the Brussels, we have the low speed in the real typical speed in the peak hour, and also in the simulation, we have formed the traffic congestion in the right places, which means that our model perfectly simulate the real peak hour data. And yeah, for the conclusion, the probabilistic travel demand model that we develop, I know it's very simplistic, but it's effective because the results of the validation shows that the accepted performance of the proposed model, and in case that you don't have the data is not available, this model might be helpful for you. And also this our study was a very good showcase that the SUMO performs very well in large scale networks, because normally we use SUMO for the microscopic simulation, and I see not that much work which use SUMO for larger scale modeling in mesoscale, and SUMO performs very well, and it takes like, I think it takes like 1 hour for every iteration of the traffic assignment for SUMO to do the simulation, which is in my point of view acceptable. The limitation of our study was that the transit traffic from other countries, for instance, the passenger cars which are, I don't know, coming from France to Netherlands and pass through Belgium, were not considered in our model. And also, when we want to select the origin and destination of the trips, we assume that the behavior of passenger cars and trucks trips are the same, which might not be the reality, because the origin and destination of the truck trips might be different from the passenger cars in reality. And also in the next step of my research, I'm going to apply. I'm going to use this base case model that I have in order to in order to evaluate the impacts of connected and autonomous vehicles on Belgium road network. And in order to do that, I'm going to use the dual iterate mix tool, which is the traffic assignment tool within SUMO that I and Jakub have developed. And this tool will can solve the multi-class traffic assignment problem. And also for the future research suggestion, I would suggest to apply the same model to any other country, here Germany, Netherlands, France, or any other place in the world, to see whether this simplistic model works in other countries, or it's or only I was lucky to see this good performance. With that, I would like to thank you very much. And this is the QR code to my LinkedIn. And if you are interested, you can scan it and stay in touch with me. And I'm interested to hear your comments and questions. Thank you.